Welcome to an overview on the principles and applications of using the t-statistic. T-testing is a form of inferential testing that allows us to make comparisons between two groups on a single numerical outcome. These groups, or samples, can be compared in three distinct situations. Compare a sample to its population of origin. For example, compare a sample of surgical patients at one hospital to all surgical patients. Compare two samples from the same population or from two different populations. For example, compare residents of Detroit to residents of Philadelphia, or males to females. Compare a sample to itself. For example, measure function in a group of injured patients and then measure function in the same group after a treatment. The common thread for all of these comparisons is that we will infer something about a population based upon what we observe in our samples. In other words, if we find differences between samples of males and females, then all males and females will likely have the same differences. Examples of practical questions that could be answered using t-tests include: is there a difference in the effectiveness of two drug treatments? Did a new teaching method produce improvements in learning? Is the average infection incidence of this year's surgeries significantly better compared to last year? There are fundamental differences in how the t-statistic can be used versus the z-statistic. The z-statistic counts on knowing the standard deviation of scores in the population. The t-statistic estimates the variance in the population by using the variance in the samples and by calculating a value called the standard error. Because this introduces additional error in determining probabilities of occurrence, we can no longer use the z-distribution to make inferences. Instead, we use the family of t-distributions. These distributions have the same general shape as a z-distribution, but the shape of the two tails of the curve will vary depending on the number of subjects in the sample. A large sample, signified by the first arrow, will have distribution that mimics the z-distribution. A progressively smaller sample will have broader tails, resulting in higher proportions of the curve being farther away from the mean compared to the z-distribution. The effect of the sample size is quantified by the degrees of freedom, essentially the number of subjects in a sample minus 1. This value is used to help determine the probability of a particular score occurring and helps mitigate the effect of different sample sizes and thus provides improved accuracy for hypothesis decisions and the inferences made from these decisions. The discovery of the phenomenon of the t-distribution and the development of the t-statistic is credited to William Seeley Gossett. He published his theories using the pseudonym Student, and thus the student's t-test was born. He developed his theories while working as the head brewmaster at the Guinness Brewery, as he looked for ways to quantify efficiency in the production of hops and production of beer. He discovered that the difference between two group means divided by the estimated variance of those scores would produce a predictable set of standard scores, and thus they would have predictable probabilities. This distribution could then be used to test the differences between sets of scores, to determine if the differences between the means was due to some level of causality or due to chance. Using the t-test to make inferences involves a four-step process. Step 1. State a null hypothesis and set an alpha level for significance testing, typically less than 0.05. Step 2. Set the critical region using the t-distribution as the criteria for your hypothesis testing. 3 factors will impact those boundaries using a t-score distribution table. The table will typically give you a t-score that you will use to set your criteria. This is known as the critical value. And this then sets the boundaries for the critical region as shown by the colored area in the tails of the curves. We typically use degrees of freedom, alpha level, and the direction of the hypothesis test to make this criteria decision. Step 3. Sample data is collected and a t-statistic is computed. Step 4. The null hypothesis is evaluated. If the t-score you calculate exceeds your critical value and can be placed in the reject region of the t-distribution, you will be able to reject the null hypothesis, as shown by the colored tails in the figure. If the t-score you calculated does not exceed your critical value, then you will be able to accept the null hypothesis, as shown by the uncolored area in the center of the distribution in the figure. The t-test can be used in three basic circumstances. To compare compare a sample to its population of origin when the population variance is unknown. This is known as a one-sample t-test. Compare two distinct samples from the same population or from two different populations. This is known as the independent or unpaired samples t-test. Compare a sample to itself. This is known as a dependent or paired samples t-test. There are specific conditions or assumptions for using the t-test, and thus ensuring the accuracy of your conclusions and inferences to the population of interest. They include simple random samples or pair of individual or paired observations, or the reasonable assurance that the samples are representative. You are comparing two groups of scores using a single numerical outcome of either ratio or interval scale. You have valid measurements with no bias in the measurement of the outcome or in the assignment to groups. A normally distributed set of outcome scores, or a moderate to large sample, is expected. Equal variances found in both groups, meaning that the variability in one group should not be substantially larger than the other group. A variation of the t-test allows us to correct for this if needed. I hope you enjoyed the video and learned something in the process. Thanks for watching.